exponential functions, and we're continuing now with the logarithmic functions. We graphed both of them last time. So today, I think it's the 20th. Okay, so let me refresh your memory about the exponential functions. Domain, negative infinity to infinity, range 0 to infinity. Here are the graphs. I'm going to graph both separately. Remember the list of, yes, Maureen, you wanted to say something? I'm sorry? It's all over the place, as you know. So it's 18.1 and 4.1. I even stopped. So they're in the correct order in my math lab. Okay, so when the base is greater than 1, and when the base is between 0 and 1. When the base is greater than 1, the exponential function looks like this. It could be 2 to the x, it could be 10 to the x, it could be e to the x, any number that is greater than 1. And as you see, it's increasing on all its domains. Last time, we graphed the inverse function. Every time you graph the inverse function and the function on the same coordinate system, you must graph y equals x. And reverse the coordinates. So we reverse the coordinates and we graph this function. This function is what it's called logarithmic function. And the base must be the same. If this is base 2, this one will have base 2. If this is base 10, this one will have base 10. If this is base e, this one will have base e. Please. Yes. Over the y equals x. Now, the other situation in which the base is less than 1, it's the same type of graph, but it's decreasing on all its domain. Like, for example, 1/2 raised to the x. If we want to graph the inverse function of this, we have to do the same thing. We have to graph y equals x first, and we will reverse the coordinates. And here's what happens. Please be careful on this one, because if it crosses the line y equals x at the same point, the inverse function will cross the line y equals x. Mandatory. This one did not have that situation because it didn't cross y equals x, but this one does. This one. So this is, of course, the log function, in short. Because it's the inverse function, the log function, as we know, will be defined and is defined. Look here. Can anyone tell us the domain of the blue function? From 0 to? Correct. From 0 to infinity, which happens to be the range, right? When we talk about the inverse functions, we simply reverse the range and the domain. So this will be 0 to infinity, and the range is negative infinity to infinity, as you see. Look at the range of the blue function, right? Everything. But the domain is not everything. It's 0 to infinity. Okay. So give me an exponential function, because we have to talk about something very important that is a property that we will be using next. Yes. Yes, please. Between? Very good question, but between what? So, yes, the blue function is the log. The brown function is the exponential. So the exponential either does this or this. The log does either this or this. They are inverses of each other, not opposites. Okay, so if you fold the paper on this line, you will see these two will overlap. This piece will overlap with this piece will overlap with this piece.
As in the same.
They will be one on top of the other. So, because they are inverses of each other, we reverse the coordinates. See? The same thing here for that one. Because we simply reverse the coordinates. This point over y equals x is here. This point over y equals x is here. This point over y equals x is here. In other words, this distance equals this distance. Everywhere. This distance equals this distance. Because we simply reverse the coordinates of all points. In other words, 2, 3, 3, 2. Very good question. Thank you. So can anyone give us an exponential function? Can anyone give us an exponential function? What about 3 to the x? Are you okay with 3 to the x? Is 3 to the x an exponential function? Is the exponent the variable? Good. So this is an exponential function. Perfect. So please give me 3 x values. 1 positive, 1 negative, and 0. Any value you want. 2. Okay. Let's say negative 3. Okay. Can anyone give us the y values corresponding to the function, corresponding to this y equals, y equals, y equals? So when x is 2, what do we get for y? I'm sorry? But we chose x. And the function is 3 to the x. I cannot just, I have to use the function. Say it again. No, it's 3 raised to x, and x is 2. What is y? Perfect. What is y next for 0? Excellent. And for negative 3? Can anyone give us the value of 3 raised to negative 3? Say it again. 3 raised to power negative 3. Just write it down. You cannot possibly, maybe you could do it in your head, but you shouldn't. Just write it down. 3 raised to negative 3. Can anyone give us? But it's negative 3. No, it cannot be negative. So 3 raised to negative 3 is 1 over 3 to the third, which is 1 over 27. So please be careful. 3 to the third power cannot be the same with 3 raised to negative 3. They cannot be the same, right? Is that clear? Okay, perfect. So now I need to show you how we go back. The notation, of course, is f inverse. What is the base of the function that we picked? Can anyone give us the base of the exponential function? What is the base of this function? Very good. So it's log the same base, log base 3 of x. So again, how do we read this? Log base 3 of x. So what do I need to show you? I need to show you that if we apply log base 3 to what? Exactly. Awesome. So I need to show you that log base 3 applied to 1 is the inverse function goes backwards, right? And I need to show you that log base 3 of is right. I didn't show you that. So I have to convince you of that. In order for me to show that, I have to explain the most, or show you the most important property here. I will say very, very important. In plain English first, any log equation can be changed or can be replaced by an exponential equation, comma, and vice versa. This is the most important concept here. Any log equation can be replaced by an exponential one, and any exponential equation can be replaced by a log one. But this is in plain English. So how does this look? How does this sentence look in math? It looks like this. Log base a of x is a number y. This is a log equation. Then we write the double equivalency symbol. What does this mean? It means that if I start here, I get that. And if I start from here, I get this. So please pay attention so we don't remember this from the very beginning, how we convert. We always start with the base, we raise it to a y, and we go counterclock back to x. A raised to y equals x. And this is an exponential equation. So we change the log equation to an exponential one, and we can change the exponential back to a log. Using this property, I hope to be able to convince you that log base 3 of 9 is, log base 3 of 9 is, I don't know. I have no idea. But I know that this can be changed into, can anyone give us the exponential equation? 3 raised to, I have no idea, equals 9. 3 raised to whatever equals 9. What should whatever be? And no other number is possible. Two indeed. So then for now we know that when we apply log base 3 to 9, we get back 2. What is the next? We apply log base 3 to 1. Let's see. Log base 3 of 1 is, I have no clue, but I know that I can change this into, when we always start with the base, going counterclockwise, tell me what to write. 3 raised to blah, blah, blah equals 1. Now let's think. There is only one number that I raised 3 to get 1. And that number is 0 indeed. I go back and I'll say, okay, I'm convinced now that log base 3 of 1 will get back 0. Finally, we have to show that log base 3 applied to what? Yeah, let's see. So log base 3 of 1 over 27. Again, I have no clue, but I know that I can change this log equation into an exponential one, and I always have to start with the base and go counterclockwise. So what should I write? Raised to blah, blah, blah equals 1 over 27. I know that this must be a negative number. Otherwise, I can't change that number into a fraction unless the power is negative. So what could that be? And it can only be one number. Negative 3 indeed. Awesome. So then, when we apply log base 3 to 1 over 27, we get negative 3. There are also two special log functions. Two special log functions. And here they are. Of course, the common log and the natural log. Exactly what we had for exponential. So common log, of course, with base 10, and natural, of course, with base e. So here is f of x equals log x. I don't see a base here. Well, that's by convention. We know it's 10. So I'll say here base 10. But we do not write the base. This is the correct notation. What about natural log? F of x is ln x. Because it comes from German. Log natural instead of natural log. So we kept it like that. So this is natural log. We don't see a base. Well, we know what the base is. What is the base of the natural exponential function? Same thing, the natural log function. So these are so important. They have both their own key right here. And that's the reason why that they are on the same key. See here? In blue with the second, it's 10 to the x, and the key is log, base 10. Here's in blue with the second, e to the x, and the actual key is ln. Why? Because e to the x and ln are inverse functions of each other, inverses of each other, and log and 10 to the x are inverses of each other. Any questions for me here? Any questions? As we mentioned earlier, the domain of the log function, let's take a look at some domain situations. Oh, sorry. Domain for log function. So if we have, let's say, f of x equals log base, just common log, base 10, of x plus 2, what should I write in order to determine the domain of this function? What do you think? So remember what we said, that any log function has to be defined on 0 to infinity, and the range is everything. What is log applied here to? What is the expression that we apply log to? Let me give you several examples. What do I apply log to in here? Can you read the expression for me? Okay, awesome. What is the log applied here to? Exactly. These quantities have to be greater than 0. For the first function, x plus 2 has to be greater than 0. For the second function, x minus 4 has to be greater than 0. The first domain is -2 to infinity because I have to write x greater than -2. For the second function, I'm going to call it g of x. The domain will be x greater than 4, so the domain for g is 4 to infinity. That's how we determine the domain of a log function. The quantity the log is applied to has to be strictly greater than 0. And I would like to, now I'm looking at this. If time allows, no, time doesn't allow in 7 weeks. Solve equation example, no, we don't have time for that. So I just want to show applications with real world applications with using logs. So we covered everything else. If we have time, we can go back and do more, and we will review, of course. Is the test okay on Wednesday? I don't mind reviewing for 2 sessions if we need to do that. If you prefer to take the test after Thanksgiving? I don't mind either. I'm more interested in grades than having to. Okay, it's up to you. But I need to know by the end of the day today. I don't have a problem with that. Okay, I'm looking at a word problem. Ready? because you may, and this is very important to see where we use this, right? So let's take a look. Let's read the problem. Students in a psychology class took a final examination as part of an experiment to see how much of the course content they remembered over time. They took equivalent forms of the exam in monthly intervals thereafter. Fine. Every month they took the exam. They took the exam at the end of the course, and then the next month, and then next month, and the following month, and the following month. The average score for the group is denoted by f of t. So that's the function, the average score for the group. After t months was modeled by. So t is in months, between 0 months at the end of the course and 12 months, so a year later. So that is a function that contains a log. You see ln, natural log. What is the base of ln, or natural log? E. E. We just wrote the base, right? It's right here. The base of ln is E. I just showed you the keys in the calculator, correct? Okay, perfect. So now let's see what they want us to do. We are going to copy the function and the time interval. What was the average score on the original exam? What am I going to do? The average score on the original exam. What do you think we're going to do? Say it again. Ask again.
What's the question?
The question is, what was the average score on the original exam? How do I determine that? When we're asked, say it again. Of course. Of course. Very good. That's all I needed you to say. Of course, the original, the initial, it's always when x is 0 unless otherwise stated. Of course. Well done. Thank you. So let's copy. So this is problem. It's from a different book. Sorry. So there is no even a point in writing why. So f of t, 88. It's the same author. I'm sure if I look hard enough, I find the same problem. This is the same author. Okay, what was the average score on the original exam? Part A. Of course, I have to find f of 0. In a minute, we'll determine that. What was the average score after 2 months? So in part B, f of 2, and so on and so forth. F of 4, f of 6, f of 8, f of 10, and f of 12 after 1 year. So here's how we construct this. I hope you have your calculators. In y equals, ready? We will type in this function, which is 88 minus 15 natural log, and in parentheses, here's the key for x right here, x plus 1. Do we have this so far? Then go to second and table set and make sure that just the independent variable is in the ask mode. Only the independent variable. Second and table set. We have that. Do we have that? Where you have it? So natural log is right here. X is right here, and plus 1. Close the parenthesis. Perfect. And go to second and table set. Make sure you set the independent. Scroll down to the right. Highlight the ask and press enter. And now go to second and table. So when we go to second and table, we're going to punch in all these numbers. So we get all the answers at once. Ready? 0, enter. 2, not 22. 2, enter. 4, enter. 6, enter. 8, enter. 10, enter. 12, enter. Because we don't want to repeat the operation. So once I have the function in. So now I'm copying the answers. 88%. I'm going to round it up to 72%, and then 64%, and then 59%, and then 52%. I missed one, 55%, and then 52%, and then 50%. So this was a real life application in which mathematicians, students, a lot of people were involved. They came up with a function, and this is what they observed. So what can you say about, yes, please.
Where's X on the chart?
Where is X? Right here. It's this key right here next to alpha, this one, xt theta n. We got it? Yes? Okay, perfect. So what do you observe? What can you say about this function? What does it show?
So
Excellent. A declining grade, for sure. What if I'm asked to graph this function? And this is the final question here. What will I do? Here's what I do. $88 is the maximum, right? 20, 40, 60, 80, 100. 88 is somewhere here. Then 2, 4, 6, 8, 10, 12. So this is time in months, and this is f of t. At 2, 72. 2, 4, 6, 72, roughly. 64. 2, 4, 6, 64. And then at 6, 59. And 8, 55. At 10, 52. And then 50. Here it is. It has to be a natural log. It has a minus in front. My points were not perfect. My units is not perfect, of course, but this is the graph. The graph of f of t, 88 minus 15 natural log t plus 1 for this. Only between 0 and 12, nothing else. Only the numbers we determined. Any questions? Okay, I would like to continue now with quadratic equations. And basically, complex numbers first. Complex numbers. What is a complex number? A complex number looks like this, where a is the real part. This whole thing is the imaginary. And I is the imaginary unit. The imaginary unit is the square root of -1, which we know it's not possible in real numbers. So examples of complex numbers will be 2 minus 3i, or 4 plus 7i, or 3i. These are all examples of complex numbers. What about I squared? So then I, again, is the square root of -1. Well, something that does not happen in real numbers, I squared will be -1. First, we would like to add complex numbers. Can anyone give us 2 complex numbers that you can think of to add? And then we are going to subtract them, multiply, and divide. And then we are going to perform some operations with square roots of negative numbers. Can anyone make up for us 2 complex numbers? Any complex numbers you can think of? Give it a shot. You can use examples I gave you, or just make two up. Very good. 1 plus 2i. And the second one? Put some negatives in there, too. Excellent. We don't really need parentheses when we add, right? I can just remove them. 1 plus 2i minus 3 plus I. And the next step is just combine like terms. I will combine 1 with negative 3, and what do I get? Very good. And then I will combine 2i with I, and I get positive. That's it. So this is the complex number that we obtained by adding those two complex numbers. Excellent. So now let's subtract. We can choose the same ones, or you can come up with others. Just give me two that you would like to subtract. All the same. We just combine like terms and distribute. Ready? The same ones or others? It's up to you. Same ones, fine. Can anyone dictate the first step in which parentheses are removed? 1 plus 2i, and then plus 3, and then I. Excellent. Combine like terms. 1 plus 3 is 4, and 2i minus I. Just combine like terms. Plus I. Excellent. Let's multiply now. Do we stick with these two, or we want to choose others? Same ones, fine. So 1 plus 2i, negative 3 plus I. We use FOIL, exactly like we would multiply binomials. How much is 1 times negative 3? Perfect. How much is 1 times I? How much is 2i times negative 3? Excellent. Now careful. Plus 2i times I. 2i. Excellent. What did we say about I squared? Because I need to replace it. Excellent. Good. Very good. So then I have negative 3. I have I minus 6i. What do I get? Excellent. And I have 2 multiplied by negative 1. Excellent. I always put the real part first. How much is negative 5 minus 2? I'm sorry, negative 3 minus 2 is negative 5, and minus 5i. And this is the product of the two complex numbers that you came up with. So if we want to multiply them, this is what we get. Any questions? Any questions? It's just using FOIL.
If it was 3i squared, would it still be negative 3?
If it's 3i squared, 3 times negative 1 would be negative 3.
Oh.
Only I squared. So if you're talking about an example with negative 3i squared, yes, this will become negative 1. Negative 3 times negative 1 will be positive 3.
Okay.
Yes. Very good. Let's see how we divide complex numbers. Slightly different than you would expect. So you want to stick with the same example? That's fine too. Yes? Okay. Which one is at the top? It doesn't matter, but you have to choose. You want to keep this one at the top and this in the denominator? Yes? Okay. This is very similar to, not the same, but the idea is similar to conjugate, complex conjugates in this case, or rationalizing. So this is a plus b. We need to use a minus b in order to get a squared minus b squared. So what will be the conjugate of this then? If this is a and this is b, and now I want a minus b in the denominator and numerator, of course. Negative 3 minus I. Awesome. Excellent. So now, I don't have enough room here, so let's determine the denominator first, because the denominator is easy. So we have, according to the formula, right, the special product, we have to square this. What do we get when we square this? That's what it says. Square A. 9. What do I get when I square I squared? Yes, but I have to see it. I have to write it for everyone first. So first, when we square I, we get I squared. Very good. So now, 1 times negative 3, because I have to multiply the numerator. 1 times negative 3, and 1 times negative I, and 2I times negative 3, and 2I times negative 1. I already performed that. Just a minute ago, we multiplied those two. Oh, I'm sorry. No, we didn't, because it's different. Sorry about that. Sorry. We have to start from scratch. Don't even look at that. Sorry, I forgot. This was the conjugate. So 1 times negative 3 is negative 3. 1 times negative I is negative I. 2I times negative 3 is negative 6I. And this times this is negative 2I squared. What do we replace I squared by again? But this is negative 1, and this is negative 1. Let's go back to the denominator first. How much is 9 opposite negative 1? Indeed. Great job. So now we have negative 3, and we have negative I minus 6I, which is negative 7I. But careful now, we have negative 2 times negative 1, which is positive 2. Awesome. How much is negative 3 plus 2? But negative, right? Negative 3 plus 2. Negative 1 minus 7I over 10. And we have no choice. We have to separate the real part from the imaginary part. So this is again A plus B times I. So it's a little bit more complicated to divide complex numbers. Slightly more complicated, right? Questions? Would you like to work on another division, multiplication, adding, subtracting, or we can move on? Okay. Let's take a look at the following. When we take the square root of 2 times the square root of 3, can I write that this is the square root of 6? Absolutely yes, this is mandatory, it's possible, because the square root of A times B is the square root of A times the square root of B. So we can go backwards and forward. So if I have this, I can write this. If I have this, I can write that. However, this is not allowed with complex numbers. So the square root of negative 2 times the square root of negative 3 is not the square root of 6. And you can say, how come? You still multiply negative 2 by negative 3, you get positive 6. True. However, this rule is valid only for real numbers. This is not a real number. This is complex, a complex number. This is not a real number. This is also complex. So then how do I perform this operation? Here's how. The square root of negative 2 will be replaced by the square root of negative 1 times the square root of 2, in which this represents what? No. I squared is negative 1. This is the square root of negative 1. So this is just I. So this is I, the square root of 2. So I simplified the first one. Can anyone tell us how to simplify the square root of negative 3 then? It will be the square root of negative 1 times the square root of 3. And this is what? So this will be I, the square root of 3. So now I can go back and replace this expression by I, the square root of 2, and this expression by I, the square root of 3, and let's see what happens. And we can prove that that's not the square root of 6. So let's take a look. So I the square root of 2 times I the square root of 3. I have to multiply the i's together. I times I is what? How much is I times I? Very good. And now, because this is a real number and this is a real number, I can multiply them. What do I get? Yes, the square root of 6. But now how much is this? Indeed. So the answer is negative the square root of 6, not the square root of 6. So what works for real numbers does not work for complex numbers. The same thing with the ratio. So let's suppose we have the square root of negative 9 divided by 4. I will have to separate it as the square root of negative 9 over the square root of 4. The numerator will be the square root of negative 1 times the square root of 9, and the denominator is the square root of 4. What is this? Very good. How much is this? How much is this? 2. So this is 3/2 I. Any questions? Why do we really talk in this class about complex numbers? Here's why. I'm debating with myself to show the property, the square root property first, and then explain why we do this. I think I'm going to do that. So the square root property. And then I'll come back to complex numbers. So the square root property, do you remember when we solved an equation like this? We said, okay, yes. What type of equation is it? Yes, perfect, but quadratic, degree 2. Perfect. How many solutions will this equation have? It will have 2 because the degree is 2. So if the degree is 2, 2 solutions. If the degree is 5, 5 solutions. If the degree is 1, 1 solution. So it's a polynomial, but it's a quadratic equation, so degree 2. So what did we do next? We factored, because now we know how. We reviewed the entire factoring procedure. How do you factor x squared minus 4? It's in descending order. It's a binomial. No greatest common factor. No negative leading coefficient. Special product. Yes. How do I factor this? Times. Perfect. X plus 2, x minus 2. So then we have 2 options. And the options are excellent. Very good. So this was what we did before, correct? Yes? Here's another way. The square root property. In that situation, whenever we have x squared equals a number, we can take the square root from both sides, the square root property. And we get x equals plus or minus the square root of that number. The plus or minus do not come from x squared. They come from the other side, or actually they do come from the x squared, not from this side, but from the square root of x squared. So then, if we want to solve this equation, like x squared minus 4 equals 0, we'll change it into x squared equals 4. We will take the square root from both sides, and we get x equals plus or minus 2 by the square root property. So then, if I want now to solve the equation x squared plus 1 equals 0, you will say, move 1 to the other side. I will comply with that. Then you will say, take square roots from both sides. You know that we have to find 2 solutions. You will take the square root from the left-hand side, which should be the absolute value. Instead, we put plus or minus. But what is this? Exactly. So that's the reason we needed complex numbers, because we couldn't solve this equation. This equation has no real solutions. This is a positive number plus a positive number. You can never find a real number that you square, which becomes positive. You add 1 to it and you get 0. It's not possible. So then complex numbers were created in order for us to solve this. So that is the taking the square root property. So let's take a look at another example. Let's say x plus 1, everything squared equals negative 16. The left-hand side is a square. The right-hand side is a number, no x. Because if I have this, then I cannot use the square root property. But I don't. I only have negative 16. So like we did before, first of all, what type of equation is it? It is quadratic, x squared, right? So we have to take the square root because it's already set up like that. What do we get on the left-hand side? Well, we get x plus 1. The right-hand side has to have plus or minus. It should come from here, the absolute value. But instead, we put plus or minus on the other side. How much is the square root of negative 16? No. Careful, no. It's not a real number. The square root of negative 16 is the square root of negative 1 times the square root of 16. The square root of 16 is 4. The square root of negative 16 is not a real number. So what is the answer? Very good. 4i. Excellent. So then x equals negative 1 plus or minus 4i. That's it. Let's look at another example. Let's say we have 2x plus 3 squared equals 4. This is already set up for taking square roots. I don't have to do anything. I will immediately take the square root from both sides. The left-hand side, 2x plus 3. The right-hand side has to have plus or minus. And now I'm asking you what is the square root of 4, and you will say the square root of 4 is 2. So now that we will obtain two solutions, as we expect. 2x equals negative 3 plus or minus 2. And then x will be 1/2, and in parentheses, negative 3 plus or minus 2. I have to separate them. So how much is negative 3 plus 2? Negative 1 times 1/2 is negative 1/2. How much is negative 3 minus 2? Divided by 2, negative 5/2. And we obtain the solutions using the taking square roots property. So how many methods of solving quadratic equations we know so far? We know factoring, and the second method is taking square roots. Okay, here's a third one. I'm sure you remember the third one from your other math courses. Ready? Quadratic formula. Quadratic formula requires us to present the quadratic equation in this form, in descending order, equal symbol 0. And then there's a simple algorithm that we have to remember. Negative b plus or minus the square root of b squared minus 4ac divided by 2 times a. Quadratic formula will solve any quadratic equation. Factoring, not. Factoring will not solve any quadratic equation because not all polynomials are factorable. But the quadratic formula will always solve. Taking square roots will always do it with, I have to show you a different method though, in between. But yes, quadratic formula will always solve. So make up a quadratic equation for us. Any quadratic equation you want. Please make up a quadratic equation so we can solve it. You just have to fill in a, b, and c with any numbers you want, and you're there. 4x squared, perfect? Yes? Very good. Let's say minus 7. Perfect. Good. Is it in descending order? How much is A? How much is B? How much is C? -7. Awesome. All you have to do is just put them in. So let's do just that. Negative B plus or minus the square root of B squared. No matter what B is, this number will always be positive. Do not ever start with something like this. That will be terribly wrong. No matter what B is, positive or negative, you have to square it. So this will always be a positive number. Minus 4 from the formula times A, which is 4, times C, which is -7. I have to put in parentheses. Instead, the negative with a -7 will change into positive, so I don't have to put too many parentheses in there. Over 2 times A, which is 8. Let's do this with the graphing calculator. This is very important and crucial to understand that in the graphing calculator, you have to have parentheses around the numerator, and you have to have parentheses under the square root. Careful how we put it in. Okay, let me stop this because